Hello students. So in this video lecture we will study branch control instructions, instructions related to the stack memory, machine control instructions, and some other special instructions present in 8085 microprocessors instruction set. We will start with branch control group of instruction. Okay. Before we start our discussion on branch control instructions, let us understand what do we mean by branch control. So branch control, to understand that, we must recall the way of instructions execution that is being performed by 8085 microprocessor. So as you know, if we consider this is our memory IC. Okay, so our memory IC has different memory locations, so memory cells, can you understand? So, and each of this cell has corresponding unique memory address. So we generally start with C000. Then the next memory address will be C001. This is the memory address. Then C002. Then C003. In this way. Okay. So now let us understand. This is a memory location. C050 maybe. Okay, so suppose here we are having dots. So this is C050, then next is C051, then next is C052. Obviously in this way it will progress this memory address. Now when microprocessor 8085, the microprocessor IC, fetches the instructions from memory, it needs the starting memory address obviously, and then it fetches the all the instructions written in the subsequent memory location. So once it fetches the instruction from C000 memory location, the program counter will be incremented by 1. So next instruction will be fetched from C001 memory location. Okay, then again program counter will be incremented by 1, and the next instruction written in C002 memory location will be fetched and will be executed. Now this is the general way of, or by default way of fetching the instructions from memory by 8085 microprocessor or by any processor. So it fetches the instructions sequentially, one by one, C000, then C001, then C002, then C003, in this way. But this branch control group of instructions can change this sequential way of program execution. So if we write some branch control instruction in C002 memory location, so here we write some branch control branch instructions. So what will happen, depending on the execution of this branching instruction, the next instructions may not be fetched from memory location C003. Okay, so it may change the way of program execution or instruction fetching. So program counter may be loaded with a different address, memory address, which is far from this C003 memory location. Okay, so it could be anything. So let us understand, let us assume that it is C050. So then what will happen, the next instruction will be fetched from this C050 memory location instead of this C003 memory location. So it will not be fetched, next instruction will be fetched from C050 memory location. Fetching will be completely shifted to this C0050. So the next instruction will be fetched from C051 memory location. Then again the program counter will be incremented by 1, and then C052 will be fetched. So in this way program sequence will now go on. So as you can see, the program sequence previously was in this case, in this position. So we have a certain branching from here, and now the sequence is going on from C050 memory location. So this is called branching. So it is actually dealing with the change of program execution. Okay, so they are very useful in order to implement if-else conditions or loop, or to implement loops. So if you often in the program we use if-else conditions or we use loops. To implement those, we need to use jump instructions or branch instructions. Okay. 8085 microprocessor, basically it has two kinds of branch instructions. One is jump and another is type call. So both of these instructions can change the program fetching or program execution. However, these two type of instructions, they have a difference. We will understand the difference later, but we need to know that both of these instructions, both of this type of instructions can be further classified into two groups. One is conditional, another is unconditional. Unconditional. It's also can be classified into conditional and unconditional. So what do you mean by conditional and unconditional? So in unconditional type of branching instructions, the program sequence shifts from a certain specific memory address, and it is always fixed. If this instruction is fetched, then program will be shifted. So next instruction, if it is written in C002 memory address, the next instruction will not be fetched from C003 memory address. It will be always shifted to a particular memory address. It's mentioned in the corresponding instruction, whether it's jump instruction or call instruction. Suppose this memory address is C050, so the next instruction always will be fetched from C050. There is no chance that the next instruction will be fetched from the next memory location C003. Always it will be fetched from the given memory address in the instruction C050 in our case. Okay, so this is the unconditional type of call instructions or jump instructions. Okay, and another type is called conditionals. So it actually, this kind of instructions actually checks the status of different flags. So it may be carry flag, it may be zero flag, it may be parity. Okay, it may be the sign flag. So depending on this 4 flags condition, the next instruction may be fetched from the next memory location C003, or it may be fetched from the specified address in the instruction itself, C050. Okay, so there is a chance that the program execution will not be hampered. The next instruction will be fetched from C003. Whereas in case of unconditional type of jump or call instructions, the next instruction will be always fetched from the specified memory address in the instruction, that is C050. So this is the difference. We will discuss first all the unconditional and conditional jump instructions, then we will discuss all the unconditional and conditional call instructions. So we will start with unconditional jump instruction, that is JMP. Okay, so its function is it jumps unconditionally. So functionality is to jump the program sequence unconditionally, or it's branch the program sequence unconditionally. So always in this jump, whether it's a jump address or a call address, it is always associated with the 16-bit memory address specifying where to jump. Okay, so that is why this kind of jump instructions or call instructions, they are always 3-byte instructions. They need the first byte among this 3 byte is always the hex code of jump, and the next 2 bytes, in the next 2 bytes we must specify the memory address. Obviously in the next memory address we must specify the lower order byte of the memory address, or lower order 8 bits of the memory address. In the next memory location, or in the third memory location, we must specify the higher order 8-bit or higher order byte of the memory address. Okay, so as it is mentioned, it jumps or it branches the program sequence unconditionally. Always after fetching this or after execution of this kind of jump instruction, JMP instructions, the program sequence will shift to the specified memory address. Let us understand this with an example. Let us understand the execution of the instruction JMP C050. So this is the unconditional jump instruction. After execution of this particular instruction, program sequence will be shifted to the memory location C050. Now let us first understand how it is written in the memory. So it should be written somewhere in the program memory. Let us assume that it is written from the memory location C000 only. Okay, next is C001. Obviously jump C050. This instruction is a 3-byte instruction. It needs 3 consecutive memory addresses in order to store the corresponding instruction. So next obviously it will be C003, and it is also assume that this is the this is the memory location C050, and next it is C051, this is C052, in this way. Okay, now first we need to write down the opcode of jump instruction, or the hex code of the jump instruction, and that is C3. So let us write down here all C3. So let's change the color. It will be, we need to write down C3 over here. Next, in the next memory location C001, we need to specify the lower order byte of the target memory address, that is C050. We need to write down lower order byte 50. In the next memory address C002, we need to write down C0. Okay, we need to store C0. So now the complete instruction is stored. Now if we specify the starting memory address C000 to the 8085 microprocessor, it will start execution of this instruction from the memory location C000, and it will first fetch this hex code C3, and will understand that gives a jump instruction. Then it will read the corresponding target memory address one by one, the lower order byte first, then the higher order byte. So in this case it stores this address memory target memory address C050 internally in the WZ register pair. So WZ register pair we have not discussed it. Why? Because this is not available to the programmer. We cannot directly use this or directly store something, some data or anything in the WZ register pair or in the W or Z individual registers. Only some of the instructions of 8085 microprocessor they uses internally this WZ register pair in order to store some address. So in LDA instruction, STA instruction, in case of LHLD instruction, this WZ register pair is used internally during the execution of these instructions to hold the 16-bit address. Also in the jump instruction already we have noticed, in case of all the jump instructions, whether it is conditional or unconditional, all call instructions, whether it is conditional or unconditional, and also in case of RST instructions, in case of return instructions, this WZ register pair is used internally to hold the memory address. Okay, so here in this particular case the corresponding memory address C050 will be stored in the WZ register pair. So in W, C0 will be stored, in Z 50 will be stored, so that the complete address is stored in WZ register pair. And then once this storing is done, now obviously the program counter now contains the memory address C003. Program counter always incremented while after fetching. So once it is fetched the C0 higher order data, higher order memory, higher order byte of the memory address from the memory location C002, program counter will increment itself automatically to the mark or to denote the next memory address C003. Okay, but in jump instruction what will happen now? In the program counter's content will not be placed in the address bus. So now the next instruction will not be fetched from the memory location C003. Why? Because the program counter's content is abandoned to be placed from the address bus. Rather, what will happen? The content of WZ register pair will be now placed in the address bus. That is why the next instruction now will be fetched from the memory location C050, and WZ, the content of WZ register pair plus 1, that is C051, will be loaded in the program counter. So now the content of program counter will be overloaded with this particular data C051. Okay, now the next the next instruction obviously will be fetched from the C051 memory location after the instruction written in C050 is fetched. Okay, in this way the sequence of program execution will continue. So as you can see, we have shifted after C002 memory location, after executing the instruction written in C002 memory location, from this to directly C050, and the sequence of execution has been changed onwards, C050, then C051, then C052, and no longer this particular sequence of execution will be used. After C003, C004, it will not be used. So we have a branch from this to this, C002 to directly C050 memory location. So as you can see, in jump C050, this particular instruction, it jumps unconditionally. So there is no chance that we do not check any condition before jumping. Always we jump without checking any condition. So if it is written somewhere, always the program execution will be shifted to the specified memory address C050. No, there is no chance that the instructions written from the C003, then C004, these memory addresses will be executed. There is no chance. Always the program sequence will be shifted. That is why it is called a unconditional jump instruction. Okay. Also, we must note that during the execution of this branch control instructions, none of the flags are modified or affected. Okay. However, status of the flag bits are read by the conditional jump instructions to take the jump decisions or branching decisions. So which flag registers are actually checked by this conditional jump instructions? The flags carry flag, sign flag, parity flag, and zero flag. These 4 flag bits are checked by the conditional jump instructions, or that we will find the same 4 flags are checked by the conditional call instructions also. And depending on this, we have 8 different conditional jump instructions. So both, we will start with this JC and JNC. So JC and JNC, these are the conditional jump instructions that checks the status of the carry flag. So JC instruction jumps to the specified memory address if the carry is 1. So it is jump on carry signal, jump on carry instruction. Okay, so if carry flag is 1, then only it will jump to the specified memory address in the instruction. Otherwise the program execution will continue in the previous order. Okay, suppose we are executing the instruction JC C050. Okay, and let us first write down this instruction in the program memory. So in the memory, let us start writing the instruction from C000 memory location itself. 1, then it will be C002, it will be C003, it will be C004, obviously, dot dot dot, somewhere there is a memory location C050, and this is next C051, the next memory location will be C052, in this way. Now to write this, we need to write down the hex code of JC instruction in the first memory location C000, and for this we need to consult the table, opcode table, and if you consult that, you will find that DA is the corresponding opcode or the hex code of JC instruction. So DA. Then in the next memory location, you must write down the lower order byte of the target memory address. So in this case, it's C050, so 50. Then higher order byte C0 of the memory address. obviously. Now we need to inform the microprocessor the starting memory address C000 of this instruction. So once microprocessor is informed, it will start fetching the instructions from C000. It will fetch the first instruction, that is DA. It will understand that it's a obviously it's a conditional jump instruction. Then it will read the next two memory locations C001 and C002 in order to read the target memory address where to jump, and it will store it internally in the WZ register pair, as we have already discussed. So it will store this memory address in the WZ register pair. Okay, now at the same time it will also check the carry. So while while it reads this particular lower order byte of the memory address, target memory address, it simultaneously checks the condition of carry, because obviously it's a condition, it's a conditional jump instruction, and moreover it's a jump on carry instruction. It will check the condition of carry flag. So let us also assume some previous value of carry flag. If the previous value of carry flag, suppose it was 0, so if the carry was 0, then obviously it will not jump to the target memory location C050, obviously. Now the program sequence of execution will now go on from memory location C003, then C004 onwards. So this will be our program execution now. The program counters content will also not be changed. Okay, and we will follow the default way of program execution without any change. Okay, so it was our default way of program execution, right? So we follow that. Okay, after C002, then C003, then we will go for C005 in this, C004 in this way. Okay, but if we consider that the content of carry was previously 1, then what will happen? Then the program counters content, which was C003, after reading the higher order byte of the target memory address from memory location C002, obviously that will not be placed to the address bus. Instead of that, the content of WZ register pair will be placed to the address bus, and that is why the next instruction will be fetched from the memory location. Just change the color. Memory location C050. Why? Because the content of WZ register pair, which was C050, and that is now placed in the address bus. So this address will be now fetched. Okay, but the program counters content, which was C003, that will also be changed by the content of WZ register pair plus 1. So that is C050. So it will be overloaded with the content C051. Okay, that is why after executing the instruction C050, the next instruction will be fetched from the memory location C051, and this will be now our sequence of program execution. So as you can see, previously this was our sequence of program execution, and now we have a branch, or we have jumped to the memory location C050 after C002 if the carry was 1. If carry was 0 previously, then this jump doesn't take place. Instead of that, we will follow the default way of program execution. After C002 memory location is read, the next instruction will be fetched from the next memory location C003 onwards. So that is why it is called a conditional jump instruction. So whether or not to jump, that depends on the condition, that depends on carry here. The condition is the carry flag here. Okay, the next instruction is the JNC instruction. As the name suggests, J for jump, NC for not carry. So this is a conditional jump instruction, and it will jump on no carry. That is, when carry flag was previously 0, in that case it will only take the jump decision, otherwise the previous order of execution will be followed. Okay. Similarly, depending on the sign flag, uh, there are two conditional jump instructions, JP and JM. JP is jump on positive. So if the if the sign flag S flag was 0, that means it was positive. Sign flag is 0 means it indicates the positive result. So if previously the sign flag was 0, in that case only JP instruction will jump the program sequence to the given memory address, otherwise the previous order of execution will be followed. In the opposite will happen in case of JM's instruction. In JM instruction it is actually jump on minus. That means if S equals to 1, if the S flag was 1 previously, then only this JM instruction will jump the program sequence to the given memory address. Depending on the parity flag, we have two conditional jump instructions, JPE and JPO. In JPE it jumps on parity even, so that is when P equals to 1 previously, then only it will take the jumping decision, otherwise it will follow the previous order of program execution. And in JPO obviously it is jump on parity odd. That means when if parity flag was 0 previously, then only it will take the jump decision, otherwise the previous order of execution will be continued. Depending on the 0 flag, we have to jump conditional jump instruction JZ and JNZ. In JZ it is actually jump on 0, so that is when 0 flag was 1, then it will take the jump decision, otherwise it will not jump. Similarly, when in JNZ, if 0 flag is 0, then only it will jump, otherwise it will not jump. Okay. The next instruction is PCHL. PCHL is also a unconditional jump instruction. So what will happen after the when microprocessor 8085 executes this PCHL instruction, it will load the program counter with the content of HL register pair. So that is why if previously the content of HL register pair was C050, suppose C0 was loaded in H register and 50 was loaded in L register, and what will happen after the execution of PCHL instruction, the program sequence will be shifted to this memory location C050. So then the next instruction will be fetched from the memory location C050, next C051, in this way. So it is also a unconditional jump instruction. It is branching the execution, the sequence of program execution from one particular memory location to another memory location. However, it is not checking any condition. It is always taking the jump decision. Okay, that is why it is called also called a unconditional jump. Unlike the jump or call instructions, this PCHL instruction doesn't need to specify the memory address where to jump. It will be internally loaded from the HL register pair. So that is why this is a 1 byte instruction. It needs only the hex code of the corresponding instruction in the to be written in the memory location in order to write the PCHL instruction. Next instruction is the call instruction. So it is a unconditional call instruction. Call, then we need to specify the 16-bit address. So that is why it is also a 3 byte instruction. The first byte is the hex code of the call instruction, and the next 2 bytes contains the memory address. Its function is unconditional subroutine call. Now there is a difference between the jump instruction and call instruction. The difference lies in the fact that when we use the jump instruction in order to jump from the memory location C002 to the memory location C050, we do not save the content of program counter, which it would have been if the jump instruction, if we do not have jumped in this particular memory location C050. That is the address of the next memory location C003. So if we did not use the jump instruction, or we did not jump in the memory location C050, we would have fetched the next instruction from the memory address C003. Then onwards you start the next instruction from the next memory location. In this way we would have progressed. But right now, due to the presence of this jump instruction, we have shifted to the memory location C050, and the next, obviously the next instruction will be fetched from the memory location C051, then C052. In this way it will progress. But in case of jump instruction, we do not save this memory address C003. Therefore, if any time in the program, somewhere later in the program, if we want to again come back to this particular memory location and execute the all the instructions written in the memory location C003 onwards, we cannot do that. But in case of call instruction, actually it saves this next memory address C003. So using the call instruction, if we jump to this particular memory address, and later on if we write somewhere in some memory location, suppose C055, return instruction, it will come back to the original program sequence, and we can now can execute the instructions written from the memory location C003 onwards. So that is the main difference between call instruction and jump instruction. We have already discussed that in call instruction, the address of the next instruction to call is stored or is saved somewhere, but where it is saved we have not discussed yet. Actually it is saved in stack memory. So this is a new term to you. This is actually the part of the same memory IC. So physically it is residing in the same memory IC, RAM memory IC, obviously, where we have our program memory and the data memory. A part of it is also dedicated as the stack memory. Okay, and in the stack memory, obviously it has a stack pointer which indicates the top of this stack. Okay, when we do not store anything, it suppose we have a stack memory, and the stack memory, the top of the stack is C099. okay, this is the top of the stack, the same memory. The starting the address of the top of the stack is C099. This address we need to store in the stack pointer in order to tell that this is the starting address of our stack. Now you know that when we store something in the stack, we store it one by one, and when we retrieve something from the stack, we can retrieve only the last thing we have stored. So it's like last in first out kind of stack. So this is the top of the stack. If you want to store something, the first thing you need to do, you need to decrement this address stored in the stack pointer. We will get the next memory address C098, and here you store something. Suppose we are storing some random value EF. We are storing EF over here. Again, if you want to store something, we need to decrement the address of the stack pointer, which is right now C098. Obviously, decrement it, we will get C097. Now store it in the store that value you want to store in this particular memory location. Suppose we are storing A, B in this particular memory cell, in the particular memory cell of the stack memory. Okay, so this is the process of how to store something in stack. Now how to retrieve something in stack. When we will read something, we can first read on this, because this is right now my stack pointer. So right now my stack pointer has been C097, changed to C097. So this is now my top of stack. Okay, now if we want to retrieve something, we can first retrieve this last stored data in our stack memory, that is the AB, and after that we increment it by 1. So now my stack pointer becomes C098. Now next thing, if we want to again retrieve something, we can retrieve this item, and again we need to increase the stack pointer. So in case of storing something in stack, we need to decrement the stack pointer and then we need to store. So the process is like that: decrement the stack pointer and then store. And if we want to retrieve something from the stack, we need to first we need to retrieve the data, read the data, read it, then increment the stack pointer. So read the data stored in stack pointer address and then increment the stack pointer, so this is the convention to use the stack memory. Okay, and you know, I think this processes we call a particular name of storing something in the stack memory, which it is called push operation, and retrieving something from the stack memory is called pop operation. We have separate instructions, push and pop, in microprocessor 8085's instruction set related to read or write something in this stack memory, that we will understand, that will go through later. But for the time being, you must understand this is the basic principle of reading and writing something in the stack memory. And for the time being, you just remember that in case of call instruction, it stores the next instruction's address, or next to the call instruction's address, in the stack memory. Now let us understand the procedures to be followed in the execution of call instruction by the microprocessor 8085. Okay, so suppose for that purpose, let us consider an example of call instruction, call C050. Okay, suppose this is the call instruction which we will be executing. Now let us also understand how to write this instruction in memory. So we have the memory IC, obviously it's a RAM memory. So in the program memory we write the instruction, and somewhere in the program memory, let us understand the first instruction of our program memory is itself the call instruction, and we are our starting memory address, you know that it's C000. Here we must store the hex code of the call instruction. Now the hex code of the call instruction is CD, hex code or opcode. Okay, then in the next memory location C001, we must write down 50, the lower order byte of the target memory address, and then in the next memory location C002, we must write down the higher order byte C0. Something may be written in C003, we do not know that. Okay, onwards, and let us also consider somewhere this particular memory address C050 is there in the memory, and next to that must be C051. Okay, C050, and next to this will be C051, and somewhere also consider the stack memory. Okay, so suppose this is our content. Suppose let us consider the content of the stack pointer prior to the execution of this call instruction was C099. Okay, and suppose this is the memory address C099. Now what the microprocessor will perform once it fetches this call instruction from the memory. So it fetches the higher order byte from the memory address C002, then it stores this memory address where the execution should be transformed, this is the C050 memory address, temporarily inside the WZ register pair. So already we have discussed the next memory address, that is C003, should be stored somewhere, should be stored in the stack memory. Okay, so that is the feature of the call instruction. That is the difference of call instruction from the jump instruction. We save the next memory address, that is C003, the next to the call instruction. Okay, so to do that we refer to the stack pointer. Obviously the stack pointer is first decremented, so SP is first decremented. Now the stack pointer will become C098. Obviously this is the procedure to store something in stack. We first decrement it and then we store it. So we store first the higher order byte of the memory address. The higher order byte of the memory address, you must carefully remember this. So higher order byte of this memory address, not this one, sorry, higher order byte of the next memory address, that is C003. So we need to store C003. So higher order byte of this address would be C0. So we need to store C0 in this particular memory location, C098. Okay. Then again we need to decrement the stack pointer and we should store the lower order byte of the memory address C0, that is 03. So we should store 03 in this particular memory location C097. So right now our stack pointer would be C097. It is holding the top of the stack. It is showing the top of the stack. Okay. Now once we store the next memory address of the call instruction, that is C003, in the stack, the next thing we should do is to move the program execution to the target memory address C050, and to do so we have already stored that target memory address C050 in the WZ register pair, and at this time, at this particular instant, what is the content of program counter we need to understand. Obviously the last instruction is fetched from the memory address C002, that is why the program counter's content will be obviously now C003. Now what will happen, this content of program counter, that is C003, it will not be now placed in the address bus, which is normal. That happens normally during the execution of any instruction. This happens, but right now in this jump in case of jump instructions and in case of call instructions, this doesn't happen in this particular machine cycle. What instead of this, what happens in the address bus, the content of WZ register pair, which is nothing but the target address, is placed. This content of program counter is prohibited to be placed in the address bus, so it is not placed. It is not placed. The content of WZ register pair is placed now in the address bus. That is why the next instruction will now be fetched from the memory location C050, and obviously, for obvious reason, the next instruction will not be fetched from the memory location C003. It will not be fetched, and one more thing happens. The content of program counter is also overwritten by the content of WZ register player plus 1. So now the content of program counter will be, if we change the color, then it will be easier to write. Now the content of program counter will be obviously C051, C050 plus 1, that is why it is C051. So after execution of the instruction written in C050 memory address, obviously as the content of program counter is now C051, the next instruction will be fetched from the memory address C051, and in this way the program execution will now go on, as you can see. So obviously it will not go into the stack memory. It must be restricted to go into the, to interfere in the, or to write something in the stack memory. We do not want that, otherwise the data stored in the stack memory will be overwritten. That we should maintain this, because this data is needed. This data may be needed later on in our program. So if we use after writing this, if we use return instruction, then the return instruction will fetch this particular memory address from the stack memory, and it will set back the original sequence of program execution, that is from the memory address C003 onwards. Okay, so for that purpose we must use return instruction, and the return instruction fetches this address stored in the stack memory. So this is the process of executing the call instruction. As you can see, this is a unconditional call instruction. Therefore, whenever if it is written in the somewhere in the memory location, always the program sequence will be transferred to the corresponding memory location C050 or whatever it is, the target memory location, and obviously before it shifts the program execution to the target memory location, it saves the next instructions address in the stack, so that later on we can come to the point of that particular instruction, and we can fetch those instructions from that particular address. Okay. Now let us discuss all the conditional call instructions. They are similar to all the conditional jump instructions. So obviously, depending on, now there is a condition. So in the previous case, in the call instruction, simple unconditional call instruction, the program sequence is always transferred to the specified memory address. But in the conditional call instruction, what happens? It transferred when the certain condition is met. And condition means we check actually the content of flag register. So which of the flag registers? Already we have seen the 4 flags: carry, carry, then sign flag, parity flag, and the 0 flag. These 4 flags are actually checked before transferring the program execution to the specified memory address. So based on that, obviously we have call on carry and call with no carry. So in call on carry, obviously CC, when the if the carry flag is 1, then only the program sequence will be shifted to the specified memory address, otherwise it will not be shifted. In call on no carry, obviously when CY is 0, then only this shifting of program execution will be done, otherwise it will not be done. Based on the sign flag, we have call on positive and call on minus. So call on positive means when S is 0, then it will call the subroutine, otherwise when S is 1, it will not call. The reverse will happen in call on minus. So when S is 1, then only it will call the subroutine, otherwise the normal way of program execution will be retained. Based on the parity, we have call on parity even and call on parity odd. We have already discussed the same thing in the jump instructions, conditional jump instructions, so I am not repeating this. And based on the 0 flag, we have call on 0 and call on not 0. Okay. All the call instructions and jump instructions are obviously 3-byte instructions. Now when we are using somewhere in our program the call instruction, we expect that the lines of our program which we have skipped by jumping to another memory location, or we often call it our subroutine. So the main sequence of program execution is skipped, and we went to the subroutine and we are executing the instructions written in the subroutine. So we always expect that line of codes which we have skipped in our main program, that will be executed later on, once we finish all the execution of all the instructions written in the subroutine. So as we have seen in our previous example, so in the C002 memory location, after C002 memory location, from the main program we have shifted to the subroutine C050 memory address, and we have retained the subroutine there in the subsequent memory location C051, C052 in this way. So we have a hope that somewhere after finishing all the instructions written in this particular subroutine, we will come back to our original stream of program execution, that is to the memory address C003. That is why we have used call instruction, because call instruction saves this particular address. Otherwise we could have used the jump instruction, because if we do not expect to come back again, then we could have used jump instruction. But we are expecting to come back again and execute all the instructions written in this main stream of program. So in the memory location C003, then C004, then onwards, okay, C005 onwards. So that is why always in the call instruction, when we use the call instruction to go to the subroutine, so this part is actually called the subroutine. So all the instructions written in this particular set of memory locations are called the subroutine. So from the main program we have shifted to our subroutine, and we are executing the instructions written in the subroutine. And at the end of this subroutine, suppose this subroutine ends at the memory address C055. So at this particular memory address we generally write the return instruction. So always a call instruction is followed by a return instruction, and the return instruction is used in order to come back the original program. So if we use the return instruction, what it will do, it will read the memory address that we have stored in the stack memory during the execution of call instruction, which we have written in the memory location C00, C001 and C002. Using these three memory locations, we have written the corresponding address of the memory location C003 obviously in the stack memory. So while we use the return instruction, it will fetch the data from the top of the stack. Obviously in the top of the stack this particular memory address is stored. Because we have the last call instruction which we have used is in this particular memory location. It was written when we shift the program execution from the C002 to C050. Okay, so that is why when we use the return instruction, it fetches the top of the stack and it will read the corresponding memory address C003, and it will store that memory address obviously for the time being in WZ register pair. As we have seen, the same thing has been done in case of jump instructions and in case of execution of call instructions also. The same thing will happen in case of the execution of return instructions. So in case of return instruction also, the memory address will be read from the stack memory, and that will be temporarily stored in the WZ register pair, and the content of the WZ register pair now will be placed to the address bus. And what will happen now, the instruction written in the memory location C003 will be now fetched, and after that the content of WZ register pair plus 1, which is nothing but the memory address C004, it will be now loaded in the program counter. So now the next instruction will be fetched from the memory address C005, and the program sequence will keep going on in this way. C004, then C05, then C06. In this way, all the instructions written in our main program, which we have skipped previously, will be now executed. So there is always a return instruction if we use a call instruction. So all call instructions has a corresponding return instructions. We must write it somewhere at the end of the subroutine. And we must also notice that this return instruction, obviously it can be of two types: return unconditionally and return conditionally. So this return instruction is unconditional return instruction, and these set of return instructions are actually conditional return instructions. And obviously as you can see, the return instructions are of 1 byte only. If we specify the hex code of return instruction, it will be sufficient. We do not need to specify anything else, because the address to which it will return, that is already stored in our stack memory, and the stack pointer holds the corresponding address, so it's not required. So it only needs a hex code. Let us also discuss the conditional return instructions. As we can see, it also depends on the four flag bits: carry flag, then the sign flag, then the parity flag, and the 0 flag. Based on that, we have return on carry, return on no carry, return on positive, return on minus, return on even parity, return on odd parity, return on 0, and return on no 0. So obviously if the condition is met in each of the cases, it will return to the main program. It will fetch the address stored in the stack memory, and it will return to the main program from the subroutine. But if the condition is not met, it will not return to the main program. Rather, the instructions written in the subsequent memory addresses after the return instruction in the subroutine will be fetched one by one, and that will be executed. Okay. Now let us discuss all the instructions related to the stack memory. So we'll start with the push instructions. Obviously push instruction stores something in the stack memory, so it stores actually the content of register pair in the stack memory. If push B instruction stores the content of BC register pair in the stack memory, whereas push D instruction stores the content of D register pair in the stack memory. Push H stores the HL register pairs content, and push PSW actually stores the content of program status word register pair in the stack memory. Now what is this PSW? PSW is actually called the content of accumulator register along with the flag register together is called the PSW register pair, program status word, and the higher order byte of this is obviously the accumulator registers content, and lower order byte is the flag registers content. So you need to understand that which one is the higher order byte and which one is the lower order byte. When we call the BC register pair or D register pair or HL register pair, the higher order byte is the B, D and H in this case, and the lower order bytes will be the E with the C, E and L. Similarly, in case of PSW, the higher order byte is the register A, and the lower order byte will be obviously the flag register. On the other hand, the pop instructions reads the content from stack memory and it will store the corresponding content in the register pairs. So we have 4 kind of pop instructions: pop B, pop D, pop H and pop PSW. So in each of them, in case of pop B, the top 2 memory locations in the stack memory will be read and the corresponding data will be stored in the BC register pair. In case of pop D, the corresponding data will be stored in the D register pair. In case of pop H, it will be stored in the HL register pair. In pop PSW, it will be stored in the A and F register pairs together. So the MSB will be obviously stored in the register A and the LSB will be stored in the F register. So how this push and pop instructions are actually executed, let us understand that with an example. Suppose we are executing the push B instruction. Before we understand or explore it later, we need to assume the initial conditions. So suppose the BC register pair contains the data 3257, so hex, obviously it's in hex. So B register contains obviously 32 and C contains 57. Okay, and also let us consider the content of stack pointer is C099. Okay, so this is the content of stack pointer, and now let us draw the stack memory somewhere. This is our stack memory, and this is the currently top of the stack, which is C099, denoted as C099 by the stack pointer. It is actually stack pointer actually denoting the top of the stack, which is C099, and this particular memory location above that will be C098, then it will be C097. In this way it will go on. Okay, now once the microprocessor will execute this push B instruction, so it will start with the MSB, storing of the MSB. So when we store something in the stack, we will first store the MSB of that, because while storing the content of while storing something in stack memory, we always decrement the corresponding address. That is why we always store the MSB first, then the LSB, such that the MSB is always stored in higher address, LSB is stored in lower address. Okay, so in this case the MSB will be stored in the higher address, that is C098, and LSB will be stored in the lower address C097, and the storing procedure is same. We first decrement the stack pointer, then we store the corresponding data. So the first step is to decrement the stack pointer. Now the stack pointer will become C098, and we will store the higher order byte, that is the content of register B, that is 32, in the corresponding memory address C098. So 32 will be now stored in that corresponding memory location. Then stack pointer will be again decremented by 1. Stack pointer will be again decremented by 1. Now the corresponding address will be C097. And in C097 we will store the lower order byte, that is the content of register C, and that is 57. So we will store 57 in the memory address C097 in our stack memory. So this is our actually stack memory. Okay, so after execution of this instruction, obviously the stack pointer's content will be C097, and this will be stored in the stack memory, and the content of register pair BC will be unchanged. And we must know that the push instructions and pop instructions, all these instructions are of 1 byte instructions. So if we want to write this instruction in memory, we need only a single byte, where we will write the corresponding hex code of that particular instruction. It will be sufficient. Now let us understand one example of pop instruction. So let us consider pop H instruction. Okay, now let us also assume some initial condition, that is stack pointer's content. So suppose the stack pointer's content is C097. Okay, and let us also do not consider any value of HL register pair. Obviously whatever it is, it will be finally changed by the contents of stack memory. Let's consider the stack memory conditions. So this is our stack memory, and suppose this is the memory address C099, this is C098, this is C097. In this way it will progress, and let us consider something is stored in C097 and C098. Let us consider AB is stored in C097 and EF is stored in C098 memory location. Okay, now once the microprocessor will execute this pop instruction, it will read the content of stack memory from the top of the stack, that is using the stack pointer's content. So obviously stack pointer's content is C097, so the first stack memory cell that will be read is the C097, and the corresponding content AB will be stored in the lower order byte of the register. So here HL register pair, so lower order byte means in the register L. So in the register L, the AB will be stored. So we must understand it right now. Okay, the higher order byte is always stored in the higher memory address, the lower order byte is stored in the lower memory address. And as you can see, C098 is higher than C097, so C097 obviously should contain the lower order byte. So it's easier to remember, and it's also the convention. So you go by the convention, it will be easier for you to remember this. You'll never get confused. So the lower order byte will be stored in register L first, and now you know that when something is read from the stack memory, the stack pointer will be incremented by 1, and now the content of stack pointer will be C098. Now the next top of the stack will be now C098, and that will be now read. The content of C098 is EF, it will be read and it will be stored in the higher order byte of the register pair, so that is the H register. So EF will be now stored in the H register, and again the stack pointer will be incremented by 1. So now the stack pointer's content will be C099. So after execution of this pop H instruction, the content of stack pointer will be C099. The content of H and L registers will be EF and AB respectively, and the content of stack memories will be unchanged. However, we must remember that right now the top of the stack is C099, that is this particular memory location. The next instructions are SPHL instruction and XTHL instruction. So both of these instructions are 1 byte instructions, and in SPHL instruction, actually it copies the content of HL register pair to the stack pointer. So it actually transfers the content of HL register pair to the stack pointer, and obviously after execution of this instruction, the content of HL register pair will remain unchanged. This is a copy paste operation. And in case of XTHL instruction, it exchanges the content of H and L register pair with the top of the stack. So the top two memory locations of the stack will exchange its data with the HL register pair. But at the end of this execution of XTHL instruction, the content of stack pointer will remain unchanged. So obviously during the data transfer operation or exchanging of the data, we'll be using the stack pointer. We need to increment it once in order to fetch the higher order byte from the from the stack memory, obviously. But at the end of the execution of this program of this XTHL instruction, the content of stack pointer will remain unchanged. Okay, so also you need to understand that in all of these instructions related to the stack memory, the push instruction, pop instruction, SPHL and XTHL instructions, the flag registers are not affected at all. So none of the flag registers are affected. Now let us understand the next group of instructions, machine control instructions. So we have two such instructions, no operation instructions and halt instruction. In no operation instruction, actually if this instruction is written somewhere in the memory, the microprocessor 8085 will face this instruction and will perform actually nothing. So this is used in order to create delay in delay subroutines. So, okay. So in both of these instructions, in no operation instruction and halt instruction, none of the flags are actually affected. In halt instruction, what happens? It halts the program execution. So the content of program counter will not be placed in the address bus and the next instruction will not be fetched. So once we write the halt instruction, so the instructions written after that will no longer be fetched. So generally that is why generally we write the halt instruction at the end of our program. So once halt instruction is executed, the microprocessor will go into the wait state. We need an interrupt or reset signal to exit from this halt state. Okay. So the next set of instructions which we will understand is called special set of instructions, special instructions. So these are CMA instruction, STC instruction, CMC instructions and DAA instruction. So let us start with the CMA instruction. CMA instruction actually complements the accumulator's content. So it inverts the content of accumulator bitwise. So previously if it was 10011110, after the execution of CMA instruction, the content of accumulator will be changed to 01100001. Okay, so it will invert the content of accumulator, as you can see. Now no flags are actually affected during the execution of this instruction CMA. The next instruction is the STC instruction. It actually sets the carry flag. So the carry flag will be equals to 1. The carry flag will be set to 1 after the execution of STC instruction. Now we need to remember only the carry flag is affected. None of the other flags are modified by the execution of this instruction. CMC instruction. CMC instruction actually complements the carry flag. So if previously carry flag was 1, it will be now 0. If it was previously 0, it will be now converted to 1. It will complement the carry flag. It also modifies only the carry flag. None of the other flags are affected by the execution of this STC or CMC instructions. Okay, and next is the DAA instruction. DAA instruction is used to change the content of accumulator from a binary value to a 4-bit binary coded decimal digits. So it's BCD, from binary to BCD conversion. If we execute this DAA instruction, then what will happen? The content of accumulator will be changed from binary value to 4-bit binary coded decimal value. So this is the only instruction that uses actually the auxiliary carry flag internally to perform this binary to BCD conversion. And during this binary to BCD conversion, all the flags are affected. Okay. So how this binary to BCD conversion is done? So let us understand that these DAA instructions are used in BCD additions actually. So when we add to BCD numbers, the result will be obviously in binary format. So to convert that binary formatted result back to the BCD format, we need this DAA instruction. Now to understand how this DAA instruction converts the binary formatted data of accumulator to the BCD format, we need to divide the content of accumulator into 4 bits, lower order 4 bit and higher order 4 bits. So the content of accumulator is actually divided into 4 bits. One is lower order 4 bit and the higher order 4 bit. So let us name this. So D0 is the LSB, D1, then D2, then D3. So D0 to D3 are the lower order 4 bits, and D4, D5, sorry, this is D5, D6 and D7. D4 to D7 are the higher order 4 bits. So the value of the lower order 4 bits D3 to D0 in the accumulator, this is the accumulator register. Obviously in the accumulator, if it is found to be greater than 9, or if the auxiliary carry flag is set, then then this particular DA instruction will add 06 or simply 6 to this particular lower order 4 bit. So it will check the condition that whether this lower order 4 bit contains a value which is greater than 9, or the auxiliary carry flag is set. If either of these two conditions are satisfied, then 6 will be added to this lower order 4 bit. Similarly, it will also check the higher order 4 bit and the corresponding result if it is greater than 9, or if the carry flag is set, if either of these two conditions are satisfied, then again a 6 will be added in the higher order 4 bit. So obviously you can understand that in the previous case 06 was added, so that the 6 should be added into the lower order 4 bit, and in this particular case 60 should be added, so that 6 can be added to the higher order 4 bits. So this is the conversion procedure. So let us understand this procedure with an example. Let us assume that add B instruction is used, suppose, to add to BCD data, binary coded decimal value data, stored in register A and register B. Okay, and then after that addition, depending on the addition result, I will show you what we mean by the simply binary data, and what is the necessity to use this DA instruction in order to convert the result back to the binary coded decimal value. Okay, so let us assume that prior to the execution of add B instruction, the content of register A was 85 in BCD. So you better understand this. It's not hexadecimal number, it's in BCD. So in BCD, that means we convert this each of this 8 first in 4-digit binary number, and we'll write this as the 4 higher order bits. So obviously it will be 1 0 0 0, and then we convert this 5 and we'll write the 4 lower order bits, so that will be 0 1 0 1. Okay, so this is now the value stored in actually register A, and we call this 85 in BCD. Obviously this is the value stored, and we call it 85 BCD in BCD, binary coded decimal value. And register B's value, suppose register B's value is 0 0 0 0 0 0 0 1 sorry 0 0 0 0 0 1 1 0 0 1 1 0. So if we consider that is also written in binary coded decimal value, then it will be obviously 06 in BCD. Okay, so in BCD number, obviously we vary from 0 to 9. It's a binary coded decimal number, so it's actually the decimal number. We do not have A, B, C, D, E and F, whereas in hexadecimal number we vary the digits from 0 to F. So this is the main difference. So now while representing the data in BCD number, obviously we can expect that none of these lower order 4 bits or higher order 4 bits are of any of these registers are greater than 9, obviously, because we have considered they are binary coded decimal digits, decimal numbers. But after the addition instruction is executed, what will happen? It will add these two numbers considering as if they are binary numbers, or they are simple hexadecimal numbers or simple binary numbers. So after the addition, the result will be, if we add simply 0 plus 1 is 1 1 1 1 0, a carry 1 is resulted. Now this is 1, no carry is actually resulted here, 0 auxiliary carry, 0 0 0 1. So as you can see, now the result that will be stored in register A after the addition operation is this one. 1000 1011, and if we try to convert this particular result in binary coded decimal numbers, and we will see that we can no longer convert it, because the lower order 4 bits are actually greater than 9. So this is obviously not a binary coded decimal number. This is a simple binary number, and it is also expected, because while adding, the microprocessor will add as if, considering as if the content of register A and B both are in simple binary numbers. They are considered to be simple binary numbers, so the result will be also a simple binary number. But to here is the requirement of using this DAA instruction, because as you can see, if we add these two numbers 85 and 06, result should be 91 in BCD. Okay, but for obvious reason, right now the result is not a BCD number, it's a simple binary number. We need to use now DA instruction after this add B instruction in order to convert this data, this hexadecimal data or simple binary data 1000 1011 from binary to binary coded decimal number. So let us understand this. So the result was 1000 1011. So obviously, if you see, the lower order 4 bits are greater than 9. So DA instruction, what will it will perform? It will add 6 with this particular number. So 6 means 0110 will be added with this. And the higher order 4 bits, obviously it is 8. So if you convert it to the decimal number, so it will be 8. So 8 is no longer to be it's lesser than 9. So, and also the carry flag was 0, so we do not need to add anything to this higher order 4 bits. So higher order 4 bits 0000 is added to the higher order 4 bits. So if we perform this addition operation, what will happen? 1 plus 1 0, carry 1 plus 1 0, carry 1 plus 1 0, carry 1, so 1001. Now if we see this number, this is a obviously binary coded decimal number, and if we try to convert it to the BCD number, we will we'll start by converting this 4 bits, and this is 1 in decimal in decimal, and if we convert 1001, it is 9 in decimal. So right now the result becomes 91 in BCD. So what we have, what originally we should have after adding the two numbers 85 and 06 written in BCD numbers. So now right now we are obtaining the correct addition of these two BCD numbers.